National Data Archive on Child Abuse and Neglect.
Hello, everyone. My name is Andres Arroyo, and I am the Archiving Assistant for the National Data Archive on Child Abuse and Neglect, or NDACAN. Welcome to the fourth session of our 2025 Summer Training Series. This session is called Exploratory Analysis, and each session this month has been building on the previous ones and are being recorded and will be posted on the NDACAN website. The National Data Archive on Child Abuse and Neglect is a project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. We are funded by the Children's Bureau, which is an office of the Administration for Children and Families. We ask that if you have a question, please enter it into the Q&A box of the Zoom interface, not the chat box. Questions will be answered at the end of the presentation, and if you need any assistance with Zoom issues, you can contact me at aa17@cornell.edu, and I will try to work with you as best I can. There's also information about Zoom at the Zoom support help site. That concludes the introductory comments. Thank you very much.
Hi, everyone. My name's Alex Roarcassi. I'm a professor of sociology and criminology at Butler University, and I'm also a research associate at NDACAN. You may recognize my voice from prior sessions this summer. It's been an exciting summer training series this year, leading a series of trainings that build on one another to illustrate the life cycle of a research project using archive data. Today, though, we're going to initiate a handoff to Noah Wan, who's a statistician at the archive. So differently than in previous sessions, I'll be working through the slides today, but then when it comes to our demonstration in R, I'll be handing things off to Noah, who will be leading the demonstration. Noah will also be leading next week's final STS presentation on finalizing your analysis and visualizing your results. So just to outline today's agenda, as I've been doing in previous meetings, we'll briefly recap last session's learnings, and then I will work through a slide deck illustrating some basic principles and strategies for exploratory analysis. This will mostly hinge on linear regression analysis and basic strategies for estimating the things you actually want to estimate using regressions. Then, as I said, I'll hand things over to Noah, who will demonstrate some of those principles and strategies in R. As a reminder, we're very excited for questions. Please drop those in the Q&A, and we will address them at the end of today's session. Okay, let's get going. What did we talk about last week? Mostly we talked about linking data. We talked about how two different kinds of linkages are possible using the administrative data that's archived at NDACAN. Among those data sets, that is to say, within our sort of data ecosystem, it's possible to link records at the individual child level. That's to say, if you find a child in AFCARS, that very same child might also appear in NCANs or in NIDID. And across those different data sets, that individual child is very likely to have an individual identifying variable that can be used to follow that individual child across multiple data sets. If you're interested in linking outside of the NDACAN administrative data architecture or environment, that's also possible, but not at the record level, not at the individual child level. Linkage to external data can be done at the aggregate level, though. So you can tabulate archive data and link it to external data at the state level, at the county level, at the year level, at the month level. You can, I suppose, link data at the aggregate level to individual level records in the NDCAN ecosystem, but you'll never be able to link individual children in archive data to individual children outside of archive data. We talked about how linkage requires very clean and well-formatted data files that share at least one identifying variable common to each data set that you link. We talked about how linkage is a useful tool for a number of different goals, for expanding our data sets, either expanding the sample size or expanding the number of variables at our disposal. We talked about how linkage can be useful in dealing with data limitations. Sometimes we can carry over values from one variable that's not missing in one source to values of that same variable that are missing in a different source. So it can be a helpful missing data strategy. Data linkage can also enable powerful research designs, particularly by allowing us to follow children over time, creating longitudinal data sets that can be particularly helpful in doing life course analysis or causal inference. Finally, we talked about how linkage can create or amplify big data problems if you don't understand the limitations in your data or do not address them appropriately. So you want to think of linkage as being both potentially very useful, but also potentially very fraught. Okay, recall also from previous sessions that our working research question that guides the research project we've been developing is this: what is the relationship between the lifetime incidence of removal and full-time employment among youth 3 years after aging out of foster care? Recall that this lifetime incidence of removal means how many times has a child over the course of their life been placed into foster care, removed from the care of their parent or caregiver and placed into some foster care setting. This variable is only measured in the AFGARs. This is why we're bringing in our AFGARs data. This is also the main predictor of interest, sometimes called our independent variable. We're most interested in the relationship between this predictor variable and some outcome. And of course, the outcome variable we're interested in is full-time employment among youth 3 years after aging out of foster care. This information is only available in NIDED, which is an administrative survey that follows children aging out of foster care. So in order to answer this question, we need linked data that identifies children in both AFGARs and NIDED and links those data so that we can study the relationship between this predictor and this outcome. Okay, let's talk now about some initial analyses that we might do once we've cleaned and linked our data. How do we start doing basic analyses to try to start answering this question? I want to emphasize that we're just going to be scratching the surface here. There's also some ways in which the strategies and principles described here don't fit our data perfectly. That's okay. This is often the case. We're just starting at the ground floor. And in any research project, you want to start there and then build up toward greater levels of complexity as you learn more about your data and the models and strategies appropriate to your question. We're going to start with a discussion of linear regression. Regression analysis, more broadly, is a statistical method for estimating the relationship between two or more random variables. And most often, we're interested in some outcome of interest or a dependent variable, and one or more predictors that we sometimes call independent variables or covariates. Now, there are all different kinds of regression analyses, regression models. Linear regression is probably the most common, and it's a powerful and flexible class of regression models, but one that includes a number of assumptions which may or may not always hold. We'll be talking about whether those assumptions hold and what the consequences of those assumptions are in today's presentation and next week's presentation. How does linear regression work? At risk of oversimplification, linear regression models essentially find the line of best fit representing the relationship between two random variables. Now you'll see I've also said hyperplane here. This is just in the case where we're analyzing the relationship between more than two random variables. For the purposes of illustration, we'll just focus on two random variables here. The most common method for estimating this line of best fit, for finding this line, is a method called ordinary least squares, which is, in most scenarios, what we call the best linear unbiased estimator. OLS essentially works by minimizing the sum of the squares of the differences, which we sometimes call the residuals, between some predicted value, in other words, the line of best fit, and the actual observed data points. Now that's kind of a word salad. Let's see if we can't illustrate this using the figure to the right. So you'll notice here that we're looking at a Cartesian coordinate plane. Usually in illustrating regression models like this, we'll put the predictor variable on the horizontal axis and the outcome variable on the vertical axis. For the purposes of illustration, it really doesn't matter what these variables are or what their units are. Each red dot represents an actual data point, some combination of two values of our predictor variable and our outcome variable. What linear regression does is essentially try to draw a line through these data points that feels like the best fit. You can look at this figure and say, that feels like a good way to draw a line through those points on average. If I were to ask you, draw a line through those points, that's about where I think most of us would draw the line. That's a little vague though, so how actually does a linear model draw that line? Well, it essentially tries out a bunch of different lines and chooses the one that minimizes the square of the distances between the red points and the blue line. There is no other line that we could draw that further reduces the sum of the squares of the distances between the red points and the blue line. This tells us that it's the best linear unbiased estimate of this relationship. Okay, what are the fundamental components of a linear regression model? Linear regressions can sometimes get very complicated. What is the most simplest version of a linear regression model? Consider the following bivariate regression. And when I say bivariate, I mean a regression that analyzes the relationship between two variables, a predictor and an outcome. Here I've drawn the model as an algebraic equation. In particular, I've used matrix notation to illustrate the structure of these data and this model. On the next slide, though, I'll back away from this matrix notation for those of you who are unfamiliar with this way of notating data structures. Usually on the left-hand side of the equation is our outcome. And here, y is a vector of outcomes that only has one variable. There's only one outcome we'll analyze. But of course, each observation or each unit has a value of that variable. And so we have a vector of outcomes that's only one across, but is as long as the number of units or observations in our sample. X is a similar structured vector of variable values, but values for our predictor variable. These are our data. These are the underlying data that we're trying to model. The rest of the regression equation are the features of our model, the parameters of our model that actually get estimated. Beta naught or beta 0 is what we call the main intercept. Essentially, this is the predicted value of our outcome when the predictor variable has a value of 0. The real thing we're interested in is estimating beta 1. And this is sometimes called the coefficient or parameter of interest. Beta 1 represents the slope of the line of best fit. So from our previous slide, beta 1 would represent the slope of that blue line. How much does it go up as it goes over? It's the main goal of a regression analysis to estimate coefficients of interest both validly, that is to say without bias, and efficiently, that is to say with precision. Epsilon is what we call the error term, and it's a vector of residuals. In other words, the distances between those red points and that blue line. It tells us essentially how much noise is there around our estimate. Okay, these are the fundamental components of a linear regression model. Let's try to notate them differently and illustrate such a model using our actual research project. Instead of using matrix notation, which can sometimes be a little confusing, we can represent the very same model using indexing. So instead of talking about vectors and matrices, we can just say that y, our outcome of interest, has a separate value for every observation indexed by the subscript I. Similarly, our predictor variable has a different value for each individual or observation indexed by the subscript I. So you see that y and x will have different values for each unit for each observation. This is not true for our parameters, our model parameters. Or rather, it is true for our residuals, but not true for our coefficients. The model will estimate one intercept and one coefficient of interest. So we'll only have one value of beta naught and one value of beta 1. Okay, recall our research question, which asks about the relationship between, total removals and full-time employment 3 years after aging out of foster care. We can substitute these variables into our model, and it would look something like this, where our outcome is current FTE, which has a different value for each child. Our predictor variable is the number of total removals, which also has a different value for each child. But our model will estimate the overall relationship between these two variables and yield a coefficient of interest beta 1 that summarizes the overall relationship across all cases. Now, because our outcome is binary, it can only take one of two values, that is to say, they are full-time employed or are not full-time employed. If we were to plot our data, it wouldn't look exactly like that Cartesian coordinate plane I showed you earlier, because the outcome variable can only have two values. There are a whole set of models that are designed specifically to analyze cases like this, where our outcome of interest has only two values. We're not going to talk about those today, though they will be introduced in next week's presentation. So that's a little teaser for next week's presentation. If you're interested in learning more about models specific to categorical outcomes, including binary outcomes, outcomes that have only two possible values, then tune in next week for a more extensive discussion of those models. Suffice it to say, though, we can use a linear model to analyze this outcome. This model is called a linear probability model. It's used commonly in a number of different disciplines. Just know that some of the illustrations I've given won't line up particularly to our example because our example outcome variable only takes two possible values. Yes or no, are you currently full-time employed? Okay, I want to offer some cautionary advice about how to interpret the results of linear regression models. You may have heard the phrase correlation does not equal causality. That may be well and good, but it's important to understand why. Recall that our research question is this: what is the relationship between lifetime incidence and full-time employment? This is arguably a little bit vague. What is the relationship? What kind of relationship are we talking about here? It's a little bit open-ended. That's partly by design, but arguably we want to be a bit more specific. What if we want to strengthen our question to something like, what is the effect of lifetime incidence of removal on full-time employment among youth 3 years after aging out of foster care? These are fundamentally different questions. They both ask about the relationship between these two variables, but the first is a bit agnostic as to what that relationship, what that association might be. The second is much more specific about hypothesizing a causal effect of our predictor variable on our outcome variable. There are a variety of reasons why results that indicate a relationship or an association between our predictor and our outcome variable do not provide evidence of a causal relationship between our predictor and our outcome variable. We won't go through all the different reasons why this might be the case. I'll just talk about the overwhelmingly most common and most problematic reason why correlation does not always equal causality. And that is the presence of some third variable that is fundamentally related to the two variables we're interested in. So say we're interested in the causal effect of our predictor on our outcome, but say there's some third variable that causes both our predictor variable and our outcome variable. Without accounting for that confounder, that third variable, our observed relationship between the predictor and outcome variable will be invalid or will be biased. Precisely in which direction and how much depends on the context. What does this look like potentially in our example research question, our example research project? Of course, we're interested in the relationship between total removals and full-time employment. Let's say we wanted to know the causal relationship between these, the causal effect of removals on full-time employment. Well, analyzing only these two variables in a bivariate regression model would probably lead to some spurious inferences about that relationship. Why? Well, consider a factor like race and ethnicity. We know that children of different ethno-racial backgrounds have very disparate likelihoods of being placed into foster care. We also know that race and ethnicity has significant impacts on people's employment prospects. There's a large literature documenting racial discrimination in labor markets. If we were to look only at removals and employment, our model would essentially have baked into it, without our knowledge, the influence of race and ethnicity both on removals and full-time employment. How do we deal with this problem of omitted variables bias? The simplest way is to incorporate information about them into our model. If we can add them to our model and model them in an appropriate way, we can, what is sometimes said, control for them, account for them, incorporate into our model the very relationship we described as a problematic confounding relationship. Now, race and ethnicity is a categorical variable, and so you should know that whenever we add a predictor variable with C categories, some number of categories C, this actually introduces C minus 1 parameters to our model, each of which measure the difference in outcomes for each category relative to some reference category. I always advise data users to choose their reference category. If you don't choose your reference category, your statistical programming software will for you, and so it's better to do it explicitly. Here, our model, though, if we were to account for race and ethnicity, would include a number of other new parameters, where we would have a separate parameter for Black Americans and a separate coefficient that measures the difference between Black Americans and white Americans. Another coefficient for measuring American, Indian, and Alaska Native individuals, Asian individuals, Native Hawaiian and Pacific Islander individuals, and multiracial individuals. Each of these parameters of interest would measure the overall difference in outcomes relative to our reference group, which we might define as white Americans. There are many, many potential confounders. Some of these we can observe, collect data about, and incorporate into our model. Many of them, though, we will not have information about and may even be impossible to collect information about. Take, for example, the relationship between foster placement and employment, which may be confounded by certain intangible features of child welfare policy and practice. Child welfare works differently in different places at different times. We have some information about this, but things like culture, personnel, institutional memory, these are not things that we can collect data about, but which influence foster placement and potentially even employment. One simple strategy for addressing unobserved confounders, or even unobservable confounders, is to introduce group-specific intercepts, or what we sometimes call fixed effects. To continue this example, if CPS systems vary across states, but are roughly stable within them over time, we can include a separate intercept for each state that will absorb all of this variation, all of this unobserved variation, and control for it. What does this look like? Well, to return to our matrix notation, our bivariate regression model looks much the same, except that we've added this parameter here. What is this parameter? S is a matrix of indicator variables where G is the number of US states. So each observation gets an indicator variable for each state. And then, apologies. And then gamma is a vector of coefficients, or what we call state fixed effects. Now, differently than our coefficient of interest, beta 1, we're not actually terribly interested in these coefficients or these parameters. We want to think about fixed effects mostly as a control that helps us estimate our coefficient of interest more validly. Under certain assumptions, for example, that the unobserved confounders at the state level do not change over time, we can include these state fixed effects, which will control for unobserved variation across states vis-a-vis their child welfare systems, but also really anything else that varies across states but is stable over time. So this is a powerful, flexible, simple way for controlling for unobserved confounders under a certain set of simple assumptions. Combining these different approaches, we might arrive at a sort of working model here of our that would be well suited to exploring our basic research question. Here we have current full-time employment 3 years after aging out of foster care. We have our model intercept. We have total removals. We have a parameter for race and ethnicity, and we have our state fixed effects. Sometimes there's a reason, though, to think that your answer might be different for different populations. For example, the relationship between removal incidence and full-time employment is very likely to be different for people who are and are not currently enrolled in school. If you're full-time enrolled in school, you're much less likely to be full-time employed. So we might want to know that. Stratification is a strategy that allows our model estimates to vary across values of a stratum variable. There's essentially two ways to do this. We can estimate our model separately for these different groups. So for example, people who are and are not in school. Or we could interact our enrollment variable with all of our other model parameters. These are functionally the same. Lastly, we might think about relaxing some of the assumptions that are built into the linear regression model. As I said earlier on, by default, linear models assume linear relationships between predictors and outcomes. While retaining the basic architecture of a linear regression model, we can relax this constraint by reformatting our variables in different ways or interacting our parameters in different ways. If you'd like more detail about these strategies, reach out and we can always talk about how to calibrate your model to best answer your research question. Lastly, a reminder, this summer training series is not focused on missing data. We have other available trainings and are always happy to provide consultation on how to deal with missing data. Missing data is a common strategy in archive data, including administrative data. A reminder that your statistical software will almost always listwise delete your records if missing values are included in your regression model. This is rarely an advisable approach to missing data, and so you always want to examine the missingness in your data, consider the mechanisms that lead data to be missing, and implement a defensible approach to dealing with missing data. If you notice in your model there are many fewer observations than in your data set, this is what's happening, and you shouldn't ignore it. Okay, that's it for my discussion of principles and strategies. And so we'll now move over to a demonstration in R. If you'll bear with me, this is going to require us to switch shared screens. Before I do, though, I just want to remind you that we're always available to answer questions. You can find my email, Noah's email, and Paige's email here on this slide. With that, let's transition over to our demonstration in R.
Thank you, Alex. 1 second, let me share my screen. Okay, can you all see my screen well?
Yes, thank you, Noah.
Okay, perfect. All right, as Alex says, I'll be handling the R coding portion for session 4 of the summer training series. My name's Noah Wan. I'm a statistician/data analyst at Indican. And we'll just be covering some of the concepts that Alex had covered in the previous presentation. So, and as always, my contact information is at the top in the header. If there are any questions that may arise after this coding portion. And of course, all data is anonymized, so any findings that we may find here are not necessarily indicative of real world data. Okay, well, let's jump right into it. So as we have before in previous iterations of the coding session, we're going to clear our environment. We're going to run some code just to make sure we have our environment is clear, of previous potential variables that were defined. We're going to load our packages, namely the tidyverse will be the most important package that we'll be using in this example for data cleaning, some graphic presentation such as ggplot2. So we can go ahead, run it, make sure it loads in. And as always, we're gonna define our working directory. So me personally, my data is located in this pathway, but when you're working with your own data, of course, create the pathways that your data is in, and we'll set our working directory and our seed for any random numbers that we may generate. All right, so as Alex stated before, simple linear regression is a very powerful tool to find correlations in our data, linear correlations, namely, and it's just a very flexible and useful tool for researchers advanced and just starting. So with that, we're going to read in our AFCARS data. And this again is anonymized data and it's not indicative of real world data. And we'll also read in just the first 20 observations to, make sure our data is read in well and see what variables we have. Okay, so it seems like the data read well. We have our ST FCIDs, we have state, a numeric state variable, a character state variable, direct numbers, date of birth, sex, race and ethnicity. We got CLINDIS, we have total removal, we have SFCMNT pay, and age at start. So these are all good variables to start with, but we'll definitely need to do a little bit of cleaning before we can throw these variables in our model. So let's look at some predictors of interest, right? So I'd say sex is a very useful variable, maybe useful to be used as a predictor, race, ethnicity, and our outcome variable for this example will be FCMNT pay, which is the monthly payment made on behalf of the child. So let's go ahead and take a look at the sex variable. So we could see that the sex variable is character, right? We have female and male, and we have a certain amount in each, which is, it's great for, reading a data in, but it's not great for putting in our model. So we're gonna have to change these to ones and zeros. As Alex said, we'll need like a reference group, which is relatively arbitrary. We can choose female or male to be our reference group, and then our one variable. So reference will be 0, and then the other variable will be 1. So let's see our race ethnicity variable as well. Okay, so likewise, we have characters, right, of American, Indian, Asian, Black, Hispanic, multiracial, white. And again, this is great for, reading a data set in, but when we put it into our model, we really want to create dummy variables, essentially binary variables that are ones or zeros that refer to a reference group. So we'll go into more detail when we create these variables, but it seems like we're going to have to make some changes for this. And our FCMNT pay, which as expected is numeric and has a large, as many different values. So this is going to be our continuous outcome for our linear regression. Okay, so as I said before, we're going to have to do some data manipulation. So for this sex variable, I want to make our female group the reference variable, and our male the other indicator variable. So essentially, in this code, I am creating a new variable called sexd, sex dummy variable, and assigning the value 1 when the sex variable is male, and assigning the value 0 when it's female. Likewise, I'm creating a Hispanic variable, kind of following this same flow, where if race ethnicity equals Hispanic, we're going to assign this value 1, and if it's not anything else, it's going to be 0. So in this second case, the reference group is non-Hispanics, right? So we're going to be comparing Hispanics to non-Hispanics, males to females with this dummy variable. And like I said, it's arbitrary. You could swap the order. It could be males could be the reference group, females could be the one value, non-Hispanics be the one value, Hispanics be the reference group. It's just our interpretation of our beta values will change with that. And I'll go into more detail as we progress. And of course, I also wanted to create an age variable from our birthday. So essentially, this line of code is just reading in the date of birth variable and just dividing it by 365.25 for leap years on average. And I also wanted to filter this data for people under 30. So just in particular in this data set, I wanted to kind of capture like the most recent iterations, most recent I suppose like children that you know, in this data set, rather than extrapolating beyond 30 years of age. Okay, so let's run this code and see what happens. Okay, I'm just gonna check some of our derived variables here. Okay, seems like it's worked. We have our females as 0 and we have our males as 1. Let's check our Hispanic variable. Okay, likewise, we have 1s are Hispanic, 0s are non-Hispanic. And we're just gonna take a look at our age, make sure it got derived correctly. Okay, looks pretty good, you know, within the age range that we expect. So we're just gonna keep moving forward. Okay, and the function I'm going to be using is the LM function. It's a linear regression model function, and we're going to assign it to this model variable. So syntax is very simple. Essentially, our outcome variable will be fcmntpay, and then we're going to follow it by a tilde, and then a list of our predictors that we want to use. So this very first one, let's try and predict the monthly payment for the children and use age as a predictor. And of course, we're going to be using our AVCARS2 variable. And then we're going to summarize it using our summary function of this model that we assigned this linear regression model to. So let's run this. Okay, so we have some output here. Just kind of a summary of our residuals and a table of our coefficients. So if you could recall Alex's presentation, we had a general equation. It's our y equals our intercept and plus beta times our beta age values. So here, I actually wrote it right here. So this is our equation to predict fcmntpay. So using these numbers that we have that the program has calculated using the least squares regression model, it shows that these estimated values are our best estimates for our betas. So this equation right here can help us predict fcmntpay based off of any given age that we have in our data set. So and I can do a quick visualization using ggplot2, just kind of plotting our age variables against fcmntpay, and then creating like that linear regression line that we saw in that presentation before. In just 1 second. It takes a little bit of time. There's a lot of data points in here, so it's gonna take a little bit. Just bear with me. Takes a little for it to load. But in the meantime, while that's loading, oh, here we go. So as you can see, we have very high density of data points here. And it's kind of hard to see because it just looks like a sea of black. But essentially there's like a higher density of points down here, and we have a slightly positive correlation between age and fcmntpay. And we find that our estimates kind of support this. We see our p-values are much greater or much smaller than the arbitrary value of 0.05. So we find statistical significance in our beta values are not equal to 0. And since our beta value for age is positive, there's a positive association between age and fcmntpay, which we can also see with this graph. Which gives us reason to believe that, you know, with increase of age, there'll be a larger FC monthly payments for these foster care children that have aged out. And yeah, we could, you know, this shows a positive correlation. So in a nutshell, linear regression kind of allows us to find these correlations between, you know, age or these continuous outcomes and our predictors. But as Alex says, this is not necessarily indicative of any causative nature between variables. It just shows us that there's a correlation. And as he said, we're going to go over potential confounders that can kind of change, that can, present complexities between correlation and the causative nature of these two variables. And one way to address this is actually to use multiple linear regression. So as Alex has said, we're going to include Hispanic status in this next model we're running, in addition to age, to kind of control for any potential confounding effects that Hispanic status might have on child monthly payment and age. So we're going to go ahead and run this second model. We're assigning it to model 2. And we're running the very same thing, except we're also adding the Hispanic variable in our predictor list. Of course, we're going to use our data as AFCARS2. We're going to run another summary model. Okay. And again, we have some information about the spread of our residuals, and we have our beta estimate tables. So it seems, we have a very similar effect here for age. And if you pay close attention, this variable is actually changed. So it's 85.594 to, well, actually, sorry, 85.6808, 6808, and it's changed slightly from 0.594. So when you add other variables in, they're not independent necessarily. It finds that best line of fit, right, that Alex was talking about, and that may slightly change our estimates, for age, since we added Hispanic status. And now we can see actually that Hispanic status, it has a negative effect on the on this model that we're running, and we can again see these p-values are much less than our arbitrary value of 0.05. So we find statistical significance for all of these not equaling to 0, essentially saying that they have a non-zero impact on the monthly payment of their the monthly FCMNT pay. And you see, I kind of wrote out this model in the same sense of this model I wrote out before. We have a positive correlation between age and FCMNT pay. We have a negative correlation with Hispanic status. Remember, the reference group is non-Hispanics, and then the 1 value is Hispanic. So when this value is 1, i.e. The participant is Hispanic, we'll have a decrease in FCMNT pay. Versus if this is a 0, they're non-Hispanic, then this whole phrase will be 0, and the effect will be null. And of course, our intercept just kind of helps us orient our line of best fit. So yeah, as Alex said, there are multiple ways to kind of control for confoundings, and another way to kind of control for another potential confounding variable is a stratified multiple linear regression, or stratified linear regression. And this is especially useful if we have reason to believe that our confounding variable violates some of our assumptions. So linearity, homoscedasticity, which we'll be going into more detail in our next lecture. But it's just kind of an alternative way to provide control for confounding variables if we can't necessarily put them into our model. So as Alex said, we're going to be stratifying by sex, actually, on this variable, the sex-d variable that we created earlier. And for this particular example, there are many ways to deal with missing data, but just for this example, for simplicity, I'll be filtering out any missing data for our sex variable, which is generally, there are other ways to handle missing data, but just for simplicity of this example, I'll just be filtering it out. So that's what this line of code does. It creates AFCARS3. From our AFCARS2 data, we're just taking out the missing sex data. And we're going to be grouping by our sex data, and we're going to be running the same model as we had before. So this group by variable runs 2 different models, one for males, one for females. And then we'll be just running the same model as we had before with FCMNT pay as the outcome, Hispanic status and age as the predictors, and our data is just referencing AFCARS3 in this example. So let's run this model. Okay, nice. And we'll be just presenting some of this summary statistics in a data frame, since it's a slightly different way of approaching this. But okay, nice. So now we have 2 different models, right? One for females, 0, and one for males, 1. And as I said, kind of arbitrary how we assign those. It's just how you want to interpret it. And I've added written forms of these models right here. And for women, we can see that we both have positive associations for age that we see, and we both have negative associations for Hispanic status, as we had seen before. But interestingly, it seems that women have a larger increase in their monthly payment compared to men as they age. So women have a larger increase of payment that they need compared to men. However, Hispanic women have less monthly payment than Hispanic men. So among women that are Hispanic, they are paying a less monthly payment compared to men. So these kind of differences kind of highlight, maybe the differences of, Hispanic status and the intersectionality of, women and men when it comes to monthly payment. And we necessarily, if sex violated some of the assumptions and we couldn't necessarily put it into our model, this is one way of addressing and controlling for male and female status or sex. And while we're still able to kind of draw conclusions from two separate models. Okay, with that, I want to leave some time for questions or Q&A. So of course, if time runs over, I have my email is noah.wan@duke.edu, but I'll just turn it over to Andreas for any Q&A. So thank you very much.
Thank you, Noah. I will read a question that arrived in the Q&A aloud, and here it is. So many child welfare related things rely on an exact age, particularly turning 18. I'm curious if folks have thought through how to write the age code to be more exact for other analyses that rely on more specific ages.
So question is like how to write the most exact age. I believe the standard, so given like date of birth information, I believe the standard is 365, like taking the number of days divided by 365.2 and dividing it by 365.25. In cases where we might not have a exact date of birth, we try and use like as much, auxiliary variable information as we can, but I believe the standard is, date of birth, number of days since date of birth divided by 365.25. If you have any more questions about, in particular about, how ages could be derived, I'm happy to answer them, of course, via email after this presentation, but I believe that's the standard.
I'll just briefly build on Noah's answer, which is a very good one. Of course, some data sets like AFGARS have information about children's date of birth. Other data sets like NCANS do not. In NCANS, we observe for each maltreatment report, the children's age in years at the time of report. But as the question asker, I think, rightly intuits, in research scenarios where it is important to know, say, the child's age in days or to know precisely when they turn 18, age in years at point of maltreatment report sometimes doesn't offer as much information as we would like to have. There's no single best strategy here. I've done different things depending on the research question, the research context, the research audience. But I would just invite folks to explore two different distributions. One thing that can be helpful is to look at the calendar frequency of maltreatment reports. So how likely are reports to occur at different points in the calendar year? And then second, to look at the calendar distribution of live births. So for the children in the cohort you're analyzing, what proportion of children were born at specific points in the calendar year? Combining information from these two distributions can help you to make inferences about the child's exact age, although of course you won't be able to observe that directly. So I hope that's a little bit helpful, if only a very partial answer. Lastly, I'll say, though, it can be yet another reason to link data. So one thing we talked about is how certain variables are available about a given child, we might have different variables in different data sets. And so if we're able to link children, say, from the NCANs to the AFCARs, we might then start to get information about their date of birth. Obviously, that limits your samples, but if you're looking for specific age data, date of birth information, linking to AFCARs might be one way to get more specific age data.
Thank you,
Thank you for
Noah
the-
and Alex. Okay, it looks like there are no more questions. So that concludes session 4 of the Summer Training Series 2025. Thank you very much to Alex Rokasi and Noah Wan for presenting. And we will have our final session next week at this time. Thank you very much.
The National Data Archive on Child Abuse and Neglect is a joint project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. Funding for NDACAN is provided by the Children's Bureau, an office of the Administration for Children and Families.